This cosmic cloud is a beautiful lie. The Crab Nebula, a remnant of a star seen exploding in the year 1054, sits 6,500 light-years away as a perfect cosmic laboratory. But within its glowing filaments are secrets that defy our very understanding of physics. By the end of this journey, you will know 25 of its most bizarre and mind-bending phenomena. We will explore sudden bursts of cosmic lightning, a spinning stellar corpse that behaves like a broken clock, and ghostly particles accelerated to impossible energies. How can a dead star's heartbeat remain so perfectly steady, and what creates flares so powerful they momentarily outshine the rest of the nebula? What does it feel like to witness a mystery that has persisted for nearly 1,000 years? At its center lies a heartbeat that should not exist. A star that exploded nearly 1,000 years ago did not die quietly. It left behind a tiny, unimaginably dense corpse, a sphere of pure neutron matter just a few miles across. This is the Crab pulsar. It spins, completing a full rotation 30 times every single second. Picture a city-sized ball of material so dense that a single teaspoonful would weigh as much as a mountain, whirling around faster than a helicopter blade. Each rotation sends out a focused beam of radiation, a lighthouse beam sweeping across the cosmos. When that beam points toward Earth, our telescopes see a flash. For decades, these flashes were so regular, so unnaturally precise, that when they were first detected in 1968, the initial thought was not of a natural object. Scientists at the Arecibo Observatory, receiving these perfectly timed pulses, seriously considered the possibility they had found an alien beacon. They even jokingly labeled the signal LGM-1 for little green men. The truth was almost as strange. They had found a stellar zombie powered by the energy of that ancient supernova, keeping time with a precision that rivals our best atomic clocks. The mystery deepens when you ask how. A spinning object in space, even one this dense, should gradually slow down as it radiates energy away. The Crab pulsar does slow, but at a rate far too gentle for the sheer power it is blasting into the nebula around it. It is like a top spinning in syrup, yet somehow maintaining its furious speed for centuries. This perfect cosmic timekeeper is a paradox, a powerhouse whose relentless rhythm defies simple explanation. And it was our first clue that the Crab Nebula was hiding far more than just a beautiful cloud of gas. But that perfect rhythm is sometimes broken. The Crab pulsar, our cosmic metronome, occasionally stutters. These are glitches, sudden and unpredictable increases in its spin rate. In a fraction of a second, the pulsar speeds up by a tiny but measurable amount, and then over the following days or weeks, it gradually relaxes back toward its normal, slowing trend. It is as if the second hand on a perfect clock suddenly jerked forward, then slowly drifted back into place. This is not a minor hiccup. It is a fundamental clue about the hellish conditions inside this stellar corpse. Astronomers believe the answer lies in a superfluid, a bizarre state of matter with zero friction that exists only under extreme pressures and cold. Think of the pulsar's interior like a hard-boiled egg. The solid, crystalline crust spins at the rate we observe, but inside, the yolk is a frictionless superfluid, spinning a little bit faster, locked away by the crust's magnetic field. Occasionally, something gives way. The crust cracks in a starquake, a seismic event on a sphere of material 10 billion times stronger than steel. Or the superfluid's vortices, tiny whirlpools of quantum fluid, suddenly unpin and transfer a massive surge of angular momentum outward. In an instant, the entire star speeds up. Studying these glitches is like doing geology on a city-sized diamond, listening for the cracks and groans from 6,500 light-years away. One of the most dramatic events happened in July of 2019. The pulsar glitched and its spin rate jumped by a significant margin. What made this event so puzzling was not just the glitch itself, but the complex recovery that followed. The data showed a multi-stage process, a wobble and a slow relaxation that no single model could fully explain. It left astronomers scrambling, forced to combine theories of quakes, superfluid vortices, and even magnetic field rearrangements to piece together a story. Each glitch is a telegram from a realm where matter is squeezed into forms we cannot replicate on Earth, a brief window into the engine room of this cosmic powerhouse. And just when we thought we understood the rules, the nebula itself began to flash. For decades, the Crab was considered a steady source, a cosmic candle whose light was powered predictably by the pulsar's relentless spin. That changed in April of 2011. The Fermi Gamma Ray Space Telescope, orbiting Earth and watching the sky in the most energetic form of light, recorded something impossible. The entire nebula, a structure light years across, suddenly flared in gamma rays. Its brightness doubled in a matter of hours. This was not a flicker from the central pulsar. This was the vast cloud of gas itself, lighting up like a cosmic strobe. Think of a city. The pulsar is the power plant at its center, with a steady hum you can set your watch by. These flares were like the entire city, every single streetlight and building, suddenly blazing twice as bright all at once for no apparent reason before fading back to normal. The sheer energy involved was staggering, equivalent to the output of our sun over several days, released in a flash, but the real mystery was location. The flares seemed to originate from a region far out in the nebula's outer reaches, far from the pulsar's direct influence. According to our best models, that is a quiet zone. The process that accelerates electrons to near light speed, making them emit gamma rays, should be too slow and gentle out there to produce such a violent, rapid burst. It is like expecting a gentle breeze to suddenly form a tornado in an open field with no storm clouds in sight. So what could possibly create such a sudden, colossal surge of energy? The leading suspect is a process called magnetic reconnection. Throughout the nebula, magnetic field lines are twisted and strained by the pulsar's furious wind. Picture those field lines as countless rubber bands stretched to their absolute limit. Sometimes they snap. When they do, they release all their pent-up energy in a catastrophic event, far more powerful than any solar flare our sun could ever produce. In that instant of reconnection, a natural particle accelerator forms, far more efficient than anything we could build. It slings charged particles to velocities so extreme they scream out in gamma rays. These flares are a testament to a hidden violence within the nebula's beautiful chaos, a reminder that even in death, a star can produce storms that dwarf anything in our solar system. Each one is a cosmic short circuit on a scale we are only beginning to comprehend. The nebula's beauty hides a ferocious motion. Look closely at a high-resolution image from the Hubble Space Telescope, and the Crab's delicate filaments are not static. They are alive, rippling with change. Thin, sharp features called wisps race outward from the pulsar, not at the leisurely pace of an expanding cloud, but at a significant fraction of the speed of light. Some have been clocked moving at half-light speed. This is not gas drifting. It is a visible shock wave, a standing tsunami of energy. The pulsar blasts out a relentless wind of charged particles, moving at nearly the speed of light itself. This wind slams into the slower-moving debris of the exploded star, the nebula itself. That collision point is a visible wall of light, a boundary where raw kinetic energy is transformed into the brilliant glow we see. The wisps are the ripples and instabilities along that shock front, the visible proof of a continuous supersonic impact happening in real time. It is a cosmic traffic jam on an unimaginable scale, where particles moving at the ultimate speed limit crash into a wall and scream out in radiation. But within this chaotic structure are stranger, more persistent features. Scattered throughout the nebula are tight, bright clumps known as knots. The most famous of these is the southwest knot, a brilliant concentration of light that stubbornly shines. These are not random clumps of gas. They are thought to be dense fragments of the original star's interior, perhaps even pieces of its iron core that survived the supernova blast relatively intact. Now they are caught in the pulsar's gale, being slowly eroded and lit up from the outside by the relentless bombardment of high-energy particles. The southwest knot glows so brightly because it is directly in the line of fire, a cosmic anvil being struck by a hammer made of light. The intricate dance between the pulsar's wind, the magnetic field that shapes it, and these dense surviving fragments creates the nebula's complex and ever-changing anatomy. We are watching a battlefield where the energy of a dead star fights against its own remains, and the wisps and knots are the trenches and fortifications drawn in light. The visible nebula is merely the tip of a colossal, invisible iceberg. What we see in optical light, those beautiful filaments and wisps, is just a small, bright inner region where the pulsar's wind collides with slower debris. Surrounding it, extending far into the void, is a massive structure we cannot see with our eyes, the true pulsar wind nebula. This is a giant bubble of ultra-relativistic particles and woven magnetic fields, all blown out by the pulsar's furious breath. It is the star's final exhalation, a ghostly atmosphere of pure energy that stretches for light years. To map this invisible giant, astronomers must use different eyes. X-ray telescopes like Chandra see the highest energy particles screaming in magnetic traps. They reveal a breathtaking structure, a luminous torus or donut of material encircling the pulsar, with powerful jets blasting out from its poles. These are not solid things, but focused beams of particles moving at nearly the speed of light, carving pathways through the surrounding space. Radio telescopes, meanwhile, trace the lower energy electrons and the nebula's outermost fringes, showing us just how vast this energetic bubble truly is. Together, these observations paint a complete portrait of a cosmic engine. The pulsar sits at the heart, its rapid spin and intense magnetic field acting like a dynamo. It generates a wind of electrons and positrons, matter and antimatter, that streams outward at nearly light speed. This wind inflates the bubble, and the magnetic field it carries organizes the chaos into a stunning architecture, channeling the energy into those brilliant jets and the glowing equatorial torus. We are witnessing a natural particle accelerator and containment system of staggering scale and efficiency. A machine built by a dying star that continues to shape its own legacy thousands of years after its death. This organized chaos leaves a distinct signature in its light. If you could see the individual waves of light coming from the Crab Nebula, you would notice something strange. They are not vibrating in all directions randomly. Instead, they show a strong preference, like countless compass needles, all pointing roughly the same way. This property is called polarization, and in the crab it is extraordinarily strong. It is the definitive fingerprint of a process called synchrotron radiation. To understand this, picture a single electron caught in the nebula's powerful magnetic field. The field acts like an invisible guide rail. The electron, traveling at nearly the speed of light, cannot travel in a straight line. It is forced to spiral wildly around the magnetic field lines. Every time it is whipped around a curve, it emits energy, screaming out a photon of light. Because the acceleration is so extreme and so directional, the light that emerges is polarized, its electric field vibrating perpendicular to the electron's spiral path. Billions upon billions of electrons, all spiraling along the same organized magnetic structures, produce the brilliant polarized glow we see. The mystery is not that the light is polarized, but what the pattern of that polarization reveals. By meticulously measuring how the polarization angle changes across every filament and wisp, astronomers can effectively draw a map of the nebula's invisible magnetic skeleton. What they find is astonishing. Instead of a tangled, chaotic mess of field lines which you might expect from a violent explosion, the magnetic field in the crab's inner regions is remarkably well ordered. It shows a large-scale structure like the orderly spokes of a wheel or the smooth flow lines around an obstacle. This beautiful organization speaks to the dominating power of the central pulsar. Its wind, carrying its own magnetic field, is so energetic that it sweeps up and combs the chaotic fields from the supernova debris, aligning them into a coherent architecture. The polarization map shows us where the magnetic field is compressed, where it is sheared, and where powerful currents are flowing. It turns the entire nebula into a cosmic blackboard, where the fundamental forces of electromagnetism have written their signature in light for us to decode. This organized magnetic skeleton is the framework for a particle accelerator of almost unimaginable power. The Crab Nebula serves as a cosmic lighthouse, not just in visible light, but in the most extreme energy regime we can detect. For astronomers studying the universe in very high energy gamma rays, the kind measured in tera-electron volts, the Crab is more than a target, it is a standard candle. Just as sailors once used the steady brightness of certain stars to navigate, modern astrophysicists use the Crab's predictable output at these energies to calibrate their most sensitive instruments. It is a reliable beacon in the murky, violent frontier of the gamma-ray sky. Yet this reliability masks a profound mystery. We know the Crab emits at these energies, but the precise dance of physics that creates such consistently powerful photons is still being unraveled. The leading explanation involves a process called inverse Compton scattering. Imagine one of those ultra-relativistic electrons spiraling madly in the nebula's magnetic field. It is already moving at 99.99% the speed of light, a particle born in a supernova and then supercharged by the pulsar's wind. Now, this electron encounters a low-energy photon, perhaps a bit of starlight or even the faint glow of the cosmic microwave background, the leftover heat from the Big Bang. In a normal collision, the more massive electron would simply knock the tiny photon aside. But at these insane velocities, the roles are reversed. The electron acts like a cosmic tennis racket, and the photon is the ball. In a violent transfer of energy, the electron smacks the lowly photon, boosting it by a factor of 1 billion or more, transforming it from a whisper of infrared or radio energy into a screaming, tera-electron-volt gamma-ray bullet. The Crab Nebula is a natural factory for this process, continuously upscaling the universe's faintest light into its most energetic signals. This makes it what scientists call a p-vatron, a natural particle accelerator capable of boosting particles to energies of a peta-electron-volt, 1 million times more powerful than the tera-electron-volt gamma rays we detect. We are likely only seeing the lower energy products of this machine, the tip of a truly monstrous iceberg. The fact that this relentless, high-energy production happens so consistently, right in our galactic neighborhood, is both a gift and a puzzle. It provides a stable reference point to study the entire violent gamma-ray universe, yet it challenges us to fully map the invisible pathways within the nebula where these ultimate collisions occur. But the Crab's influence extends far beyond what we can easily see. Surrounding the brilliant, structured chaos of the main nebula, space telescopes have detected a faint, ghostly glow in X-rays. This is the anomalous X-ray halo, a diffuse shroud of energy that envelops the entire known structure like a cosmic fog. Its very existence is a clue that our map of the nebula is incomplete. The halo's light is different, softer. In X-ray astronomy, a soft spectrum means lower energy photons. The main nebula blazes with hard, high-energy X-rays, produced by the youngest, most energetic electrons fresh from the pulsar's violent acceleration. The halo's softer glow suggests something else entirely. It is the whisper, not the scream. One compelling theory is that this halo represents an older population of electrons. Imagine the nebula's history as a continuous, 1,000-year-long storm. The particles we see in the bright central regions are like the driving rain at the storm's heart, recently accelerated and full of fury. The halo, then, could be the gentle drizzle that has drifted to the outskirts. These are electrons that were energized long ago, perhaps even in the initial supernova blast itself. Over centuries, they have slowly diffused outward, losing energy as they travel and interact with the nebula's magnetic field. By the time they reach the halo's vast distances, they have cooled, emitting only these softer X-rays as a final, fading signature of their ancient journey. They are the cosmic retirees of the Crab, settling into a quiet, expansive glow. Another, even more profound possibility exists. This faint X-ray shroud might not be from the pulsar's wind at all, but from the supernova's original shock wave itself. When the star exploded, it sent a titanic blast wave of debris racing outward at millions of miles per hour. That forward shock created the visible nebula's outer shell. But in such explosions, there is also a reverse shock. Think of it like an echo in a canyon. The initial shout races outward, but some of the sound energy bounces back from the canyon walls toward you. In the Crab, as the expanding debris slams into the stationary interstellar medium, a shock wave can actually travel backward, back into the expanding material. This reverse shock could be re-energizing particles far from the central engine, creating this faint, encompassing halo. If true, the halo is not just a faded remnant of the pulsar's work, but a direct, ghostly echo of the supernova's first moment, a fingerprint of the explosion's raw power still visible in X-ray light after 1,000 years. It is a cold case file from a cosmic crime scene waiting to be read. This ghostly halo is not the only feature that refuses to stay still. The very heart of the Crab Nebula, the brilliant optical glow we so often admire, is itself a living, breathing entity. That iconic image captured by a telescope is just a single frame from a movie that has been playing for 1,000 years. The optical synchrotron nebula, the part powered by those spiraling electrons, is in a constant state of flux. Its brightness flickers, and its intricate structures of wisps and filaments shift and dance over timescales of mere days. If you could watch a time-lapse compiled from years of observations, you would see the nebula pulse and writhe like a living thing. Wisps race outward from the central pulsar, brighten to a fierce intensity, and then dissolve back into the general glow. Knots of light change in prominence, and the entire inner region seems to throb with an unseen rhythm. This is not an illusion. It is a direct, visible consequence of the dynamic violence at the nebula's core. Remember, the optical light is synchrotron radiation, produced by electrons whipping around magnetic field lines at nearly the speed of light. The brightness of any given spot depends on two things: the number of high-energy electrons present and the strength of the local magnetic field squeezing them. Both of these factors are anything but constant. The pulsar's wind is not a smooth, steady breeze. It is a gale with gusts and lulls, delivering fresh batches of ultra-relativistic particles in uneven bursts. These particles flood into the nebula, lighting up regions as they arrive and then fading as they lose energy or drift away. At the same time, the magnetic field itself is a turbulent, twisting tapestry. As the pulsar wind slams into the nebula, it compresses and amplifies the field in some areas, making the electron spirals there tighter and more furious, causing a localized brightening. In other regions, the field may relax or tangle, dimming the light. What we see as a changing nebula is a real-time readout of this chaotic energy flow. It is a cosmic light show driven by the most powerful engine in our galactic neighborhood, a visible testament to the fact that in the Crab Nebula, even beauty is a form of furious motion. Far beyond the brilliant, churning heart of the nebula lies a silent echo of the original cataclysm. Enveloping the entire structure we have been discussing is a vast, faint shell of radio waves, a ghostly outline of the supernova's true scale. This is the blast wave itself, the leading edge of the titanic shock that ripped through space in the year 1054. While the inner nebula is powered by the pulsar's relentless wind, this radio shell is the fossilized imprint of the explosion's first unimaginable push. It is the actual bubble of compressed interstellar gas, still expanding outwards at thousands of kilometers per second, a 1,000-year-old shock front slowly dissipating into the galaxy. Its faint, ethereal glow in radio telescopes presents a puzzle. In most young supernova remnants like Cassiopeia A, this forward shock is a brilliant, rippling ring in multiple wavelengths, a sharp boundary between destruction and the undisturbed void. The crab's shell, by contrast, is whisper quiet. Why is the signature of such a violent event so subdued? The answer likely lies in what the star exploded into. Before its death, the progenitor star was probably a massive Wolf-Rayet type, which spends its final millennia shedding its outer layers in a powerful stellar wind. This wind carves out a low-density cavity in the surrounding space. When the star finally went supernova, the blast wave did not slam immediately into a dense wall of interstellar gas. Instead, it rushed out into this pre-cleared bubble, a cosmic hallway with very little material to sweep up and shock into glowing. The shell is faint because it is expanding into a near vacuum, a testament to the star's own final act of clearing its room before the grand finale. Yet this ghost is not perfectly round. The radio shell shows subtle lumps and asymmetries, a slight egg shape. This distortion is a frozen moment, a clue from 1,000 years ago. It tells us the original explosion was not perfectly spherical. Perhaps the collapse of the star's core was lopsided, or the jet of material from the newborn neutron star punched out in one direction more forcefully than another. The shape of this faint radio ghost maps the very first instance of the supernova, an asymmetry imprinted on the expanding shock wave and preserved for millennia. Studying its subtle contours is like reading the wrinkles on a 1,000-year-old face, each one telling a story of the violent birth that created everything we see within. But the nebula's chemical recipe holds a glaring omission. When we analyze the light from those beautiful, glowing filaments, we can break it down into a cosmic ingredient list, identifying the specific elements present by their unique spectral fingerprints. What we find is a composition rich in helium and lighter elements, but with a startling and significant absence, the heavy metals iron and nickel. This is deeply puzzling. The Crab Nebula is the remnant of a core collapse supernova, the explosive death of a massive star. In its final moments, such a star is like a layered onion. Fusion in its core has progressed through successive stages, burning hydrogen into helium, helium into carbon and oxygen, and so on, all the way up to silicon. At the very center, under unimaginable pressure and heat, silicon fuses to create the ultimate ash, iron. Iron is different. Fusing iron does not release energy, it consumes it. So when an iron core grows too massive, it catastrophically collapses under its own weight, triggering the supernova explosion. Theoretically, this process should blast newly forged iron and nickel, the stable end products of that silicon burning, out into the surrounding nebula. The Crab, however, seems to have skipped this final step. Its chemical signature suggests a star that exploded before its core could cook up a full batch of these heavy elements. One possibility is that the supernova itself was unusually low energy. Perhaps the progenitor star was on the lower end of the mass range for such explosions, or the collapse dynamics were inefficient. In this scenario, the explosion lacked the oomph to fully ignite and eject the silicon layer, leaving much of the potential iron unformed and still locked in the collapsed core. It was a stellar death that fizzled at the last moment, at least in terms of heavy element production. Yet there is another, more intriguing possibility. What if the iron is there but hiding? The brilliant optical and X-ray light we see comes from extremely hot gas. Iron, however, radiates most efficiently at much higher temperatures. If the newly synthesized iron from the explosion managed to cool rapidly, perhaps by mixing with cooler outer layers of debris, it could exist in a state too cold to glow in the wavelengths we typically observe. It would be a shadow component of the nebula, a missing piece of the puzzle sitting right in front of us, invisible to our current eyes. This iron-nickel deficiency is more than a curious detail. It is a direct challenge to our models of how stars die and seed the galaxy with the building blocks for planets and life. The Crab Nebula, it seems, may have broken the rules of cosmic chemistry. Scattered throughout the nebula are streaks of cosmic shrapnel. While most of the crab expands in a grand, unified motion, certain filaments are rebels, racing ahead at speeds that defy the general flow. These are the high-velocity ejecta, and they are not part of the graceful, pulsar-powered ballet we see in the inner nebula. They are fugitives launched in the initial supernova blast itself and still carrying that raw, explosive momentum. Clocked at several thousand kilometers per second, these streaks of gas are like bullets frozen in mid-flight, having traveled for nearly 1,000 years. Their incredible speed is a direct measurement of the violence of that single, catastrophic moment when the star's core collapsed. To put that in perspective, at 3,000 kilometers per second, one of these filaments could travel from Earth to the Moon in about 2 minutes. They are not being pushed by the pulsar's wind, they are running from it, forever ahead of the slower expanding shell. By carefully tracking their positions and motions backward in time, astronomers can perform a kind of cosmic forensics. They can trace these streaks of light back to a single point in space and time, effectively pinpointing the exact location and moment of the supernova's detonation. It is like finding scattered pieces of a shattered vase, and by noting the direction they flew, determining precisely where and how hard it was dropped. But these filaments are more than just speedometers. Their chemical composition is the real treasure. Spectroscopy allows scientists to read the elemental signature of this fast-moving gas. What they find are the pristine products of nuclear fusion that occurred in the star's deepest layers just before it died. Some filaments are rich in helium, others in oxygen or neon, each representing a different shell of the progenitor star, like the layers of that cosmic onion, violently peeled apart and hurled into space. By mapping which elements are moving at which speeds and in which directions, astronomers can begin to reconstruct the final, chaotic moments of the collapse. Was the explosion symmetric, blasting all layers outward evenly? Or was it a messy, lopsided affair with jets of material from the newborn neutron star punching through specific layers and spraying them in particular directions? The pattern of these high-speed filaments holds the answer. They are the fossilized trajectories of stellar shrapnel, and by reading their paths, we are effectively watching a slow-motion replay of a star's death, frame by frame, from 1,000 years ago. The story of this stellar explosion is written not just in light but in human history. In the year 1054, a new star blazed in the constellation of Taurus, visible even in broad daylight for 23 consecutive days. This was no secret. Meticulous court astronomers in China and Japan recorded its brilliant, unmoving presence with awe, noting its color as reddish-white and its fading over nearly 2 years. Islamic scholars in Baghdad and Constantinople likely saw it too, their observations woven into later star catalogues, but the most haunting connection lies far from these great empires, across the Pacific Ocean in the arid canyons of the American Southwest. Here, the ancestral Puebloan people, often called the Anasazi, had a deep cultural practice tied to the heavens. Their calendar was marked by a crucial ceremony known as the New Fire Ceremony, a ritual of renewal that coincided with the reappearance of the Pleiades star cluster just before dawn. This event typically fell in late October or early November, a time we now associate with Dia de los Muertos, the Day of the Dead. In the summer of 1054, something unprecedented happened. The brilliant new star, our supernova, would have risen in the pre-dawn eastern sky, outshining every other point of light. For the sky watchers at places like Choco Canyon or the Wupatki Pueblo, this celestial omen appeared at the very time they were preparing for or conducting their most important ritual. The coincidence is too powerful to ignore. Did they see it as a divine ancestor arriving, a great spirit lighting the way for the souls of the dead? We may never know their exact thoughts, but the physical evidence is etched in stone. At several sites, including a famous panel at the White Mesa petroglyphs, there are rock art symbols that some archaeologists interpret as a depiction of this event. A large circled star symbol is shown next to a crescent moon. Astronomical reconstruction confirms that on the morning of July 5, 1054, the crescent moon was positioned exceptionally close to where the supernova appeared, a once-in-a-lifetime alignment. This potential rock art record transforms the Crab Nebula from a distant object of study into a shared human experience. It connects the furious physics of a collapsing star to the wonder of a shaman watching the sky a millennium ago. The light that reached their eyes is the same light our telescopes analyze today, making the crab a rare bridge between astrophysics and anthropology, a cosmic event that left its mark not only on the interstellar medium but on the human imagination. The light we see tells only part of the story. If we shift our gaze to the infrared portion of the spectrum, the Crab Nebula reveals another layer of its mystery. It glows with a warmth that does not quite fit. The brilliant synchrotron radiation from those spiraling electrons explains most of the nebula's light, from radio waves up to gamma rays. But in the infrared, there is an excess, a persistent, extra glow of heat that the synchrotron process alone cannot account for. It is as if you calculated the exact output of a powerful light bulb, only to find the room is also being warmed by a hidden space heater. This infrared warmth is the signature of something solid and ancient, dust. Not gas, but trillions upon trillions of microscopic grains, each one smaller than a particle of smoke, floating within the nebula and soaking up the intense optical and ultraviolet light from the central regions. Once they absorb that energy, they re-radiate it as a gentle, pervasive infrared heat. The existence of this dust is not the puzzle, its origin is. Where did these solid particles come from in the aftermath of one of the universe's most violent events? A supernova is a furnace of destruction, a blast of energy and shock waves powerful enough to tear molecules apart and vaporize any pre-existing solid material. Yet the crab's infrared excess suggests dust not only survived but perhaps was even created in the chaos. One possibility is that this dust is a relic, a survivor from a comet time. Before it exploded, the progenitor star likely went through a phase where it shed its outer layers in powerful stellar winds. Those expelled layers, rich in heavier elements like carbon and silicon, could have cooled and condensed into vast clouds of dust grains, forming a dusty cocoon around the dying star. When the supernova finally happened, the innermost shock wave might have swept up and compressed this pre-existing dust, heating it just enough to make it glow in the infrared without completely destroying it. The dust we see today would then be a fossil, a preserved remnant of the star's final millennia. The other, more astonishing possibility is that the dust formed in the explosion itself. As the supernova ejector expanded and cooled in the months and years after 1054, conditions in certain dense, sheltered pockets might have become just right for atoms to stick together and form these microscopic solid seeds. In this scenario, the supernova did not just destroy, it also forged the very building blocks of future planets in its own wreckage. The infrared excess is a thermal whisper from these tiny solids, a clue that even in total catastrophe, the universe finds a way to begin building again. The question of which story is true, survivor or newborn, remains locked in the warm glow of that infrared light. That pervasive infrared warmth is not the only hidden layer of light. Shift your vision to the far ultraviolet, and the Crab Nebula's true outer boundary snaps into sharp focus. Observations from space telescopes like Hubble reveal a startling feature, a brilliant, razor-thin rim of light tracing the nebula's outermost edge. This is not the gentle radio shell or the diffuse X-ray halo. This is a cosmic burn scar, an ultraviolet skin where the violence of the past meets the present. It marks the exact location where the supernova's forward shock wave, a wall of debris and energy that has been traveling for nearly 1,000 years, is actively plowing into the undisturbed interstellar medium. Think of a speedboat racing across a still lake. At the very front of the boat's bow, water is violently pushed aside, churned into a frothing, turbulent spray. The ultraviolet rim is that spray, but on a stellar scale. The interstellar medium is not empty. It is a thin soup of hydrogen and helium gas with about 1 atom per cubic centimeter. As the supernova blast wave, still moving at thousands of kilometers per second, slams into this gas, it does not gently push it. It hits with such force that the gas is compressed, heated, and ionized almost instantaneously. Atoms are stripped of their electrons in the collision, and when those electrons finally recombine with atomic nuclei, they scream out their energy in the ultraviolet part of the spectrum. This creates that intensely bright, sharp edge. It is a visible boundary of ongoing destruction and creation, a real-time laboratory for studying shock physics. The temperature at this thin skin is astronomical, soaring to millions of degrees. Yet it is a fleeting heat. The gas at the shock front cools rapidly as it expands away from the collision point, its brilliant ultraviolet glow fading as it joins the broader, cooler shell of the remnant. This ultraviolet rim is therefore a transient phenomenon, a living marker of the shock's current position. By measuring its shape and brightness, astronomers can gauge the density of the interstellar medium the crab is expanding into and calculate the precise energy of the original explosion. It is a cosmic speedometer and pressure gauge all in one. Every photon from that bright edge is a direct messenger from the ongoing collision between a dead star's final act and the silent fabric of the galaxy itself, proving that even after a millennium, the explosion is not a relic but an active, advancing event. The identity of the star that died remains an unsolved case. For decades, astronomers thought they had a clear suspect. To create a supernova that leaves behind a neutron star, the progenitor must be massive but not too massive. The textbook answer pointed to a star between 8 and 10 times the mass of our Sun. A star in this range lives a short, furious life, burning through its nuclear fuel in tens of millions of years. Its core, once it fuses silicon into iron, collapses. The outer layers crash down and then rebound in a titanic explosion, while the core crushes itself into a city-sized neutron star. This neat story seemed to fit the crab perfectly. We have the nebula and we have the pulsar, case closed. Yet, the evidence we have gathered from the crime scene does not fully match this simple profile. The chemical fingerprints in the nebula's filaments, the very elements we discussed, tell a story of their own. They show an abundance of helium and a puzzling lack of iron, signatures that are hard to square with a straightforward explosion of an 8 solar mass star. It is as if we found a murder weapon, but the forensic details at the scene suggest a different sequence of events entirely. This discrepancy has forced a re-evaluation of the entire case. Could the star that died have been wearing a disguise? One compelling new theory suggests the progenitor was actually much more massive, perhaps 15 or even 20 times the mass of our Sun. Such a colossal star would have lived a life of extreme drama. In its final millennia, powerful stellar winds, radiation pressure, and violent eruptions would have stripped away its bloated outer hydrogen envelope long before the core collapsed. By the time it went supernova, it was essentially a naked, compact wolf-rayet star, its outer layers already shed into space. This would explain the nebula's chemical makeup, rich in helium and processed elements from deeper layers without the expected hydrogen signature. The explosion we witnessed in 1054 was not the death of a giant, but the final act of a star that had already spent centuries unraveling itself. The other tantalizing possibility involves a partner in crime. What if the progenitor star was not alone? Many massive stars are born in binary systems, dancing a gravitational tango with a companion. This cosmic dance can be deadly. As the more massive star evolves and expands, it can transfer material onto its partner, effectively losing mass. Alternatively, a close encounter could lead to a stellar merger, a chaotic event that fundamentally alters the star's structure and future. A binary history could neatly explain why the Crab's explosion seems atypical. The star that collapsed may have had its life and death altered by a companion we can no longer see, perhaps flung away by the supernova's kick or itself having evolved into a faint, distant stellar remnant. The pulsar we see today, with its precise spin, might be the lone survivor of a broken partnership. This ambiguity transforms the Crab from a simple textbook example into a profound cosmic puzzle. Its beautiful nebula and relentless pulsar are the end results of a stellar life story we are still piecing together from scattered clues. The mass of the original star is not just a number, it is the key to understanding the entire narrative, from the star's birth in a stellar nursery to the precise moment its heart stopped beating. And right now, the evidence points to a biography far more complex and intriguing than we ever imagined. The pulsar's relentless spin is powered by a furnace of unimaginable heat, yet it presents a profound thermal mystery. X-ray telescopes, which can peer past the nebula's brilliance to measure the temperature of the neutron star's surface itself, reveal something counterintuitive. The Crab pulsar is hot, blazing at around 1.5 million degrees Celsius, but it is not as hot as it should be. According to some of our best models for how these stellar corpses cool, it is running a significant fever deficit. A newborn neutron star forged in the supernova's heart begins its existence as an inferno with internal temperatures in the billions of degrees. Over millennia, it must cool down, radiating its primordial heat away into space. The primary cooling mechanism is thought to be the emission of neutrinos, those ghostly, nearly massless particles that barely interact with matter. In a standard cooling scenario, certain nuclear reactions in the star's dense core produce a flood of neutrinos that escape effortlessly, carrying thermal energy away like a cosmic coolant. The Crab, however, seems to be cooling faster than this standard picture allows. Its surface temperature is lower than the prediction, suggesting its internal engine room is losing heat at an unexpectedly brisk pace. This discrepancy is not a flaw in our observations, it is a clue. It points to something extraordinary happening in the pulsar's core, where matter is crushed to densities so extreme that atomic nuclei cease to exist. Here, protons and neutrons themselves may break down into a soup of their constituent quarks, a state of matter called quark matter. Or the entire core may have become a superfluid, not just in pockets, but as a unified quantum sea. Both of these exotic states would act as super-efficient neutrino factories. In a quark matter core or a pervasive superfluid, the processes that generate neutrinos could be vastly more potent, creating a relentless drain of energy from the star's heart. Imagine the difference between cooling a hot pie by simply leaving it on a windowsill versus plunging it into a bath of liquid nitrogen. The exotic core is that liquid nitrogen bath, accelerating the cooling process by orders of magnitude. The Crab pulsar's slightly cooler temperature is therefore a thermal whisper from a realm of physics we cannot recreate. Our most powerful particle colliders can only produce these conditions for fleeting instants in microscopic volumes. The neutron star sustains them in an object the size of a city for thousands of years. By measuring its temperature, we are indirectly taking the core's temperature, probing for the signature of matter in its most degenerate and strange form. This cooling enigma transforms the pulsar from a simple clock into a natural laboratory for quantum chromodynamics, the theory that governs the strong nuclear force. Each X-ray photon from its surface carries encoded information about the ultimate fate of crushed matter, asking us if we are brave enough to decode the answer. The pulsar's clean, powerful signal suggests a remarkably tidy aftermath. In the chaotic wreckage of a supernova, not all of the exploded material escapes to infinity. Gravity, the very force that triggered the collapse, often reaches back out to claim some of the debris. For many young neutron stars, this results in a fallback disk, a swirling ring of gas and dust that did not quite achieve escape velocity. This material spirals back down over centuries, accreting onto the neutron star's surface and often producing distinctive X-ray emissions. It is a cosmic mess left on the floor after the party, slowly being cleaned up. The Crab pulsar, however, shows no such sign. Our most sensitive searches have found no clear evidence of a persistent fallback disk around it. Its environment, while turbulent, appears to be dominated by the pulsar's own outgoing wind, not by any significant inflow of returning material. This absence is a silent but telling clue about the nature of this particular stellar death. One compelling explanation lies in the sheer ferocity of the pulsar's wind. Remember, this is a gale of radiation and particles moving at nearly the speed of light, emanating from a rapidly spinning, intensely magnetic object. If any fallback material did begin to condense into a disk in the centuries immediately after the explosion, the pulsar's wind, once it fully activated, would have acted like a cosmic leaf blower. It would have swept that tenuous disk away, pushing the material out to join the general nebula before it could settle into a stable, accreting structure. The pulsar's dominance is so complete that it prevents its own resupply. Another possibility points to the geometry of the explosion itself. A fallback disk typically forms when a supernova explosion is slightly asymmetric or fails to impart enough kinetic energy to all its debris. Some chunks and streams of gas are left on marginal orbits, teetering between flying away and falling back. But if the Crab supernova was exceptionally clean and symmetric, a nearly perfect spherical blast, it could have given virtually all the ejector a clean, one-way ticket out of the gravity well. In this scenario, the material received such a uniform, powerful kick that almost nothing was left lingering in the zone of uncertainty. The absence of a disk, then, would be a signature of a supremely efficient explosion. This cleanliness has profound implications. It means the pulsar we observe today is essentially running on its birth energy alone, the rotational power imparted during its collapse. It is not being fed or altered by a late-arriving dinner of fallback matter. This purity makes the Crab a more controlled laboratory for studying the intrinsic behavior of an isolated neutron star. Every glitch, every flicker of its radiation can be traced back to processes within the star itself or its direct wind, not complicated by the messy dynamics of an accretion disk. The missing disk tells us that sometimes when a star dies, it does so with a decisive finality, leaving its core to spin down in splendid isolation, its story written only in the perfect, uninterrupted rhythm of its beams and the nebula they illuminate. This relentless particle acceleration has a profound impact far beyond the nebula's visible boundaries. The Crab is not just a light show, it is a cosmic ray factory, one of the most efficient natural particle accelerators in our entire galaxy. Every second, its furious processes fling electrons and positrons into the void at energies that dwarf anything humanity can create. Our most powerful machine, the Large Hadron Collider, smashes protons together with a peak energy of about 13 tera-electron volts. The Crab Nebula routinely boosts particles to energies millions of times greater, into the realm of peta-electron volts. To grasp that scale, imagine the difference between a firecracker and a thermonuclear bomb. The mechanism is a two-stage natural supercollider. First, the pulsar's intense magnetic field acts like a colossal electromagnetic slingshot, imparting a tremendous initial kick to particles in its immediate vicinity. These pre-charged particles are then injected into the nebula's main acceleration zone, the standing shock wave where the pulsar wind slams into the slower debris. Here, in a process known as diffusive shock acceleration, particles can bounce back and forth across the shock front countless times, gaining a little more energy with each crossing, like a tennis ball being volleyed between two approaching rackets. This can boost them to those staggering peta-electron-volt energies. While we directly observe the brilliant light from the accelerated electrons, a greater mystery involves protons. The nebula is almost certainly accelerating atomic nuclei as well, but these neutral particles do not produce the same telltale synchrotron glow. Instead, they escape the nebula entirely, joining the vast, invisible sea of galactic cosmic rays that perpetually rains down on our solar system. These are the high-energy nuclei that constantly pelt our atmosphere, some with energies so extreme their origin is one of astrophysics' greatest puzzles. The Crab is a prime suspect for producing the lower energy end of this cosmic ray spectrum. When these accelerated protons eventually collide with other atoms in the interstellar medium, they can produce gamma rays and, crucially, neutrinos. This is where multi-messenger astronomy comes in. By combining observations of the Crab's gamma rays with data from neutrino telescopes like IceCube at the South Pole, scientists hope to catch a smoking gun. A neutrino detected from the Crab's direction, coincident with a gamma ray flare, would be the definitive proof that protons are being accelerated there, linking this beautiful nebula directly to the invisible particle background that fills our galaxy. For now, the factory's full output remains hidden, its most powerful product slipping away into the darkness, silent and unseen, except by their potential to create other, ghostlier messengers. This immense structure may not be expanding into a perfectly uniform void. Look at the Crab's overall shape, that ragged, elongated form stretching across the sky. While much of its asymmetry comes from the pulsar's wind and the original explosion, a subtle, galactic-scale force might also be at work. Some astrophysicists propose that the nebula's very outline is being sculpted in part by the tidal pull of the Milky Way itself. We think of tides as an ocean phenomenon, the moon's gravity pulling on Earth's waters, but on a cosmic scale, everything feels a tide. Our galaxy is a massive gravitational well, and its pull is not uniform. The force is stronger on the side of the nebula closer to the galactic center and weaker on the side facing outward. This difference creates a stretching effect, a gentle but persistent tug that could be slowly molding the expanding cloud of debris. Imagine a balloon being inflated not in empty space, but within a gentle, invisible current that flows from the heart of the galaxy outward. One side of the balloon would stretch slightly more than the other. For the Crab, this means it might be expanding into an interstellar medium that is itself shaped by these galactic tides, creating a subtle density gradient in the surrounding space. The nebula would expand more easily into the thinner regions and be slightly slowed by the denser ones, leading to its elongated, somewhat lopsided appearance. This idea, known as the tidal disruption shadow, is a profound reminder of context. The Crab Nebula is not an isolated island in space. It is a resident of a dynamic galaxy, and even this titanic remnant, born of a star's catastrophic death, must obey the broader, quieter rules of its galactic neighborhood. Its shape could be a fossilized imprint of the Milky Way's gentle, billion-year-old gravitational field, a whisper that even in the most violent local events, the grand architecture of the galaxy still has the final say. The Crab's giant flares offer a unique key to one of astronomy's greatest modern puzzles. For over a decade, scientists have been captivated by fast radio bursts, or FRB. These are incredibly brief, intensely powerful flashes of radio waves that come from galaxies billions of light years away. They last only milliseconds, but in that instant they can outshine entire galaxies. Their origin is one of the biggest mysteries in space, with theories ranging from magnetars, which are highly magnetic neutron stars, to cosmic collisions and even speculative alien technology. While the Crab Nebula itself does not produce classic FRBs, Its own violent gamma-ray flares provide the closest and most detailed local analogy we have. Think of it this way: if FRBs are the distant, unexplained explosions we hear echoing across the universe, the Crab's flares are a similar type of explosion happening right in our own cosmic backyard, where we can study the wreckage in exquisite detail. The underlying engine for both phenomena appears to be the same catastrophic process: magnetic reconnection. In the Crab, we can actually see where this happens and measure the aftermath. We observe how twisted magnetic fields, strained to their breaking point by the pulsar's furious wind, suddenly snap. This snap releases a colossal burst of energy that accelerates particles to near light speed in an instant, creating the sudden, intense flare across the electromagnetic spectrum. This is a scaled-up version of what happens on the Sun during a solar flare, but with energies quadrillions of times greater. For distant FRBs, astronomers suspect a similar drama is unfolding, but on an even more extreme stage. A highly magnetized neutron star, perhaps in a dense environment or interacting with a companion, might experience a catastrophic magnetic reconnection event or a starquake so violent it shakes the star's magnetic field, launching a brief, unimaginably energetic blast of radio waves. The Crab serves as our only nearby model for this kind of physics. By studying how magnetic energy converts to particle acceleration and radiation in the Crab's well-mapped environment, physicists can build and test the models they then apply to those faint, fleeting signals from the edge of the observable universe. Every time the Crab flares, it is not just lighting up its own nebula, it is sending us a detailed blueprint for the kind of cosmic short-circuit that might, in a faraway galaxy, announce itself as a millisecond blip that captivates the world. Understanding this local laboratory helps us decode the whispers of extreme physics from across the cosmos, turning mysterious bursts into readable messages about the most violent forces in creation. The nebula's light carries a hidden message in its colors. When astronomers pass that brilliant glow through a spectrograph, they do not see a simple rainbow. Instead, they see a forest, a dense thicket of thousands of sharp, bright lines, each one a precise barcode for a specific atom. This spectral line forest is the nebula's chemical fingerprint and its internal weather report, written in the language of physics. Every spike of light corresponds to an electron making a quantum leap within an atom of oxygen, sulfur, argon, or neon, elements forged in the star's heart and blasted into space. The sheer richness of this forest tells us the nebula is a periodic table in gaseous form. But these lines are more than just labels. Their exact brightness, their width, and their subtle shifts reveal the local conditions inside each glowing filament. A broad, fuzzy line indicates atoms being jostled at high speeds, signaling high temperature or turbulent motion. The relative strength of lines from different ionization states, like oxygen 2 versus oxygen 3, acts as a cosmic thermometer and pressure gauge. It tells scientists the temperature is around 10,000 to 20,000 degrees Celsius in the filaments, and the density is a few thousand particles per cubic centimeter, a vacuum by Earth standards but quite dense for space. This data creates a detailed map of the nebula's internal state. The central puzzle is how these conditions are maintained. The pulsar bathes the entire nebula in an unrelenting flood of high-energy radiation, powerful enough to strip electrons from atoms over and over again. This radiation field should completely dominate, creating a simple, uniform ionization pattern. Yet the spectral forest shows a complex, layered reality. Some regions are highly ionized as expected, but others show atoms clinging to more of their electrons, suggesting pockets of cooler, denser gas. This means the story is not one of simple baking by the central engine. To explain the forest, astronomers must invoke a dynamic dance between two brutal forces. The first is photoionization, where the pulsar's ultraviolet and X-ray photons directly blast electrons off atoms. The second is shock heating, where the supersonic wind colliding with slower debris violently compresses and heats the gas at the shock fronts, ionizing it through sheer collision energy. The intricate patterns in the spectral lines are the result of these two processes intertwining, with fresh shocks continually plowing into cooler condensations of ejecta. Modeling this requires sophisticated computer simulations that track every photon and particle collision. The spectral forest is therefore a cosmic Rosetta Stone. By decoding its intricate patterns, we are not just listing ingredients, we are reading the detailed recipe for how a dead star's energy cooks its own remains, a recipe written in the quantum signatures of light itself. This intricate map of light reveals a deeper structural oddity. If you trace the motions of all those high-speed filaments backward, you can calculate a single point, the geometric center of the supernova explosion from 1054. It is the spot where the star's heart gave out. Now look at where the Crab pulsar sits today. The 2 points do not align. The pulsar is offset, displaced from the explosion's true center by a distance that would take light about 2/10 of a year to cross. This is not a measurement error, it is a cosmic crime scene clue. The pulsar, the collapsed core of the dead star, is not resting peacefully at the site of its birth. It is fleeing. Precise tracking shows it is moving, a motion astronomers call proper motion, at a staggering speed of about 150 kilometers per second. That is over 300,000 miles per hour. This is the aftermath of a cosmic cannon shot. When the star's core collapsed, the supernova explosion was not perfectly symmetrical. A slight imbalance in the detonation, perhaps a powerful jet of neutrinos blasting out in one direction more than another, acted like a rocket engine attached to the newborn neutron star. The recoil from this asymmetric blast gave the dense stellar corpse a ferocious kick, launching it on a high-speed journey through the wreckage of its own making. Think of a bullet fired from a gun. The gunpowder explodes in the chamber, propelling the bullet forward while the gun itself recoils backward. In this celestial version, the exploding star is the gun, and the pulsar is the bullet blasted out of the geometric center of the blast. We are witnessing the slow but relentless departure of the murderer from the scene of the crime. Over centuries, this proper motion has carried the pulsar through the nebula, and it will eventually leave it entirely, destined to wander the galaxy alone as a high-velocity rogue. This offset is a permanent record of the supernova's final, lopsided moment, a frozen vector pointing back to the instant when symmetry broke and chaos took the wheel. It proves that even the most fundamental events in the universe carry a signature of beautiful, violent imperfection. This high-speed escape is mirrored by a deeper, more fundamental rhythm. The Crab pulsar's heartbeat is not a single, simple beat. While its radio pulses are the steady metronome we first discovered, its pulse in ultraviolet and X-ray light tells a different, more complex story. The rhythm is the same, 30 times a second, but the shape of each individual pulse is subtly altered. In radio, the pulse is a sharp, narrow spike. In ultraviolet and higher energies, it broadens, becoming a wider, more structured peak. This is not a flaw in the signal, it is a crucial clue. Each wavelength of light is produced in a slightly different part of the pulsar's violent magnetosphere, the intense magnetic field that surrounds the star like an invisible cage of force. The radio waves are thought to be generated farther out, in the more structured outer magnetosphere. The higher energy ultraviolet and X-ray photons, however, are born in the furnace much closer to the neutron star's surface, right above its magnetic poles. The difference in pulse shape is a direct map of these different birthplaces. A narrow radio pulse suggests a tightly focused beam from a specific region. The broader, more complex high-energy pulse indicates the emission comes from a larger, more turbulent area, perhaps a hotspot on the star's surface heated by a torrent of particles raining down from the magnetosphere. Even more telling is the phase shift. The peak of the ultraviolet pulse does not line up perfectly with the peak of the radio pulse. it arrives at a slightly different time in the 30 times a second rotation. This tiny offset is a geometric treasure. It allows astronomers to triangulate. By measuring the precise delay between the radio flash and the X-ray flash, scientists can estimate the altitude, the height above the neutron star's surface where each type of light is created. It is like listening to the same echo from two different points in a canyon. By timing the delay, you can locate the source of the sound. These high-energy pulses are therefore a direct probe into the engine room, a way to see the structure of the magnetic funnels above the poles where matter is accelerated to near light speed and radiation is forged. Each ultraviolet photon carries a coded message about the conditions in a place where gravity bends light and magnetic fields are 1 trillion times stronger than any we can make on Earth. By decoding the pulse profiles across the spectrum, we are not just listening to the dead star's heartbeat, we are performing a cosmic ultrasound, building a three-dimensional image of the most extreme physical environment in our galactic neighborhood. That offset pulsar is a runaway engine, but its most profound product is invisible. The Crab Nebula's magnificent light show, from radio whispers to gamma-ray screams, is orchestrated by an unseen conductor, a magnetic field of almost unimaginable strength. This is not a gentle cosmic breeze, but a structured, raging storm of magnetic force woven through every filament and wisp. Its energy density is staggering, and its very existence presents one of the nebula's most fundamental puzzles. Where did such a powerful, well-ordered field come from? It is far too strong to be merely the leftover magnetic field of the progenitor star compressed by the explosion. If you took the sun's magnetic field and squeezed it into the volume of the crab, you would still fall orders of magnitude short. This field was not inherited, it was born anew in the catastrophe. The leading explanation invokes a cosmic dynamo, a self-amplifying engine born from chaos. Think of the turbulent expansion of the supernova ejector in the first few years after the explosion. As this hot plasma churned and sheared, with different layers sliding past each other at different speeds, it could have acted like a gigantic electrical generator. Moving conductive fluid, threaded by even a weak seed magnetic field, can stretch and twist that field, transferring the energy of motion into magnetic energy. This process, called a turbulent dynamo, may have amplified a faint initial field into the powerful web we see today, but the story does not end there. The central pulsar now dominates the scene. Its rapid spin and intense wind act as a second, relentless dynamo. The wind itself carries the pulsar's own magnetic field outward, injecting fresh, organized magnetic energy directly into the heart of the nebula. This pulsar wind dynamo continuously combs and reinforces the larger field structure, maintaining the remarkable order we observe in the polarization maps. It is a two-stage cosmic creation, first a violent birth in turbulent fire, then a lifelong shaping by a spinning heart. This magnetic architecture is not decorative, it is functional. It is the essential framework that channels the pulsar's raw power. The field lines act like invisible rails, guiding the flood of high-energy particles and focusing them into the brilliant jets and torus. They contain the relativistic plasma, preventing it from simply dissipating into space too quickly. And they are the whips that force electrons into their tight spirals, making them scream out in synchrotron light. Without this powerful, organized magnetic field, the Crab Nebula would be a dim, shapeless cloud. The dynamo problem asks us to understand how chaos breeds order, and how a dying star can weave the invisible threads that will hold its legacy together for millennia. Solving it is key to unlocking the true nature of every pulsar wind nebula in the cosmos, each one a testament to magnetic force sculpting light from darkness. All this furious energy and light is a temporary brilliance. The Crab Nebula, as we know it, will not last. The relentless spin of its pulsar, the very engine powering this cosmic spectacle, is slowly but surely running down. Every glitch, every particle it accelerates, every photon it produces, is paid for with a tiny bit of its rotational energy. Over timescales that dwarf human history, that spin will continue to decay. In perhaps 10,000 years, the pulsar's wind will weaken significantly. In 100,000 years, it may cease entirely. When that happens, the lights go out. The brilliant synchrotron nebula, the glowing heart of the crab, will simply fade from view. The high-energy electrons will lose their energy, their spirals will loosen, and they will stop screaming out in X-rays, visible light, and gamma rays. The intricate architecture of wisps and knots, the luminous torus and jets, all of it will vanish into darkness. What will remain is the ghost, the vast, faint shell of radio emission. The expanding bubble of debris from the original supernova blast will continue its slow journey outward. It will become an almost invisible ripple in the interstellar medium, a cold, quiet echo of the cataclysm witnessed in 1054. This future ghost is the final, humbling phenomenon. It ties the nebula's vibrant, violent present to its inevitable, silent future. We are not looking at a permanent monument. We are witnessing a brilliant but fleeting phase in a long cosmic evolution, a firework caught at the peak of its explosion. The crab's entire story, from the death of a star to the fading of its afterglow, reminds us that even the most powerful forces in the universe are transient. Our great fortune is to be alive in the brief cosmic moment when its heart still beats, when its magnetic storms still rage, and when its light still carries the secrets of matter pushed beyond all limits. The Crab Nebula is far more than a beautiful cloud of cosmic wreckage. It is a relentless puzzle box, a natural laboratory where the universe conducts its most extreme experiments right before our eyes. We have journeyed through 25 of its strangest phenomena, from the perfect alien heartbeat of its pulsar to the sudden, inexplicable flares that light up its vast expanse. We have seen how it defies the rules of chemistry, hides exotic states of matter in its core, and accelerates particles to energies that dwarf our greatest machines. This single object challenges our understanding of quantum mechanics, tests the limits of Einstein's theory of relativity, and offers a front-row seat to the life, death, and chaotic afterlife of a star. Every glitch, every wisp, every ghostly halo is a piece of a larger, still unfinished story. The crab reminds us that the universe is not a quiet, static place. It is a dynamic arena of violent forces and beautiful mysteries, and this nebula is one of our most precious guides, so keep looking up and keep questioning. Which of these 25 strange phenomena fascinated you the most? Was it the pulsar's glitches, the missing iron, or the ancient light witnessed by cultures across the globe? Let us know in the comments below, and if you crave more journeys into the heart of space's greatest mysteries, be sure to subscribe. The cosmos is waiting, full of wonders just as strange and compelling as the crab.